Hi, I welcome you all to the first part of this lecture series on semiconductor devices. Today, I'll be enlightening you on the topic Zener and Avalanche breakdowns. I'm Dr. Yunus Jerusha, an assistant professor of physics. What is a p-n junction diode? A diode can be defined as a two-terminal electrical component with the terminals being the anode and the cathode. There are different types of diodes available in the market which are fabricated with semiconductor elements, namely silicon and germanium. The p-n junction is formed by the combination of the p-type and the n-type semiconductor material. The combination of the p-type and the n-type regions creates the depletion region. The width of the depletion region depends on the doping of the p-type and the n-type semiconductor material. Diodes usually come in glass or plastic cylindrical packages marked with a stripe on one side to indicate polarity. In a perfectly ideal diode, the current flows in one direction only, from the anode, the positive side, to the cathode, which is the negative side, and is marked with a stripe. The schematic symbol is a triangle pointing towards a bar, where the current flows in the same direction towards the barred or the striped end. The basic function of the diode is it allows the current flow in one direction only and blocks the current flow in the reverse direction. Here we see the diode in a simple circuit in the forward bias condition. If we hook up this diode in a simple circuit such as this with a variable voltage source and a current limiting resistor, we can measure the current I through the diode when a given voltage V is applied across it. Let us see the IV characteristics of the p-n junction diode. For an ideal diode, no current at all passes when the voltage is less than 0. The diode completely prevents reverse current flow. For a small positive voltage, which is the forward bias, a tiny amount of current may flow and a very large amount of current will flow above a given threshold. The amount of current that flows is actually exponential with increasing voltage. In real diodes, when the voltage is increased, a very small amount of current called the leakage current may flow, and more significantly, each diode is rated for a certain maximum amount of reverse voltage. If you apply voltage more negative than this limit, the diode will undergo a reverse breakdown and begin to conduct a significant amount of current, but in a direction backwards from the normal direction of the diode current flow. For a regular diode, we would say that the diode has failed miserably if it begins to conduct current in that direction. Therefore, breakdown occurs when the diode is reverse biased. There is an increase in the width of the depletion region while an increased current flows. This indicates a decrease in resistance, and an electrical breakdown can occur for any material like a conductor, insulator, semiconductor due to two types of occurrences, Zener as well as avalanche breakdowns. The main difference between these two is the occurrence of their mechanism due to the high electric field and the collision of flowing electrons with the atoms. Both the breakdowns can happen concurrently. This presentation gives an overview of the difference between the Zener breakdown as well as the avalanche breakdown. What is a Zener diode? A Zener diode can be defined as a special kind of diode when we compare with other diodes. The flow of current in this diode will be in the forward direction or in the reverse direction. The Zener diode includes an individual and heavily doped PN junction which is intended to perform in the reverse bias direction when a particular voltage is reached. This diode contains a reverse breakdown voltage for current conducting as well as continuous operation in the mode of reverse bias without getting smashed. In addition, the voltage drop at the diode will remain stable over an extensive voltage range and is one of the main characteristics which makes this diode suitable for utilizing in voltage regulation. Let us see some of the equivalent circuit symbols of the Zener diode. This is the circuit symbol of an ideal Zener diode. And here we have that for an actual Zener diode. Some applications of the Zener diode are: it is used as a voltage regulator, meter protector, and also a wave shaper. Let us see about Zener breakdown now. If the material is heavily doped, the width of the depletion region becomes very thin. The phenomenon of Zener breakdown occurs in the very thin depletion region. The thin depletion region has more number of free electrons. The reverse bias applied across the PN junction develops the electric field intensity across the depletion region, and the strength of the electric field intensity now becomes very high. This electric field intensity increases the kinetic energy of the free charge carriers. Thereby, the carriers start jumping from one region to the other. These energetic charge carriers collide with the atoms of the p-type and the n-type material, producing electron-hole pairs. The reverse current starts flowing in the PN junction, because of which the depletion region becomes entirely vanished. This process is known as Zener breakdown. In Zener breakdown, the junction is not completely damaged. The depletion region regains its original position after the removal of the reverse voltage. Here we see a detailed picture of the reverse bias characteristics of the Zener diode. As the reverse voltage VR is increased, the reverse current IR remains extremely small up to the knee of the curve. The reverse current is also called as the Zener current IZ. At this point, the breakdown effect begins. The internal Zener resistance, also called the Zener impedance, represented by Z with a suffix Z, begins to decrease as the reverse current increases rapidly. Let us now see about the avalanche diode. What is this avalanche diode? An avalanche diode is intended to experience the breakdown at a particular reverse bias voltage. This diode junction is mainly designed for avoiding the concentration of current, so the diode will not damage with a breakdown. Avalanche diodes are utilized as support valves to control the pressure of the system to save from overvoltages. The symbol of this diode as well as the Zener diode are nearly similar. What is an avalanche breakdown? In general, avalanche means a rapid flow of snow down a slope. Now, in a normal diode, when the reverse bias increases, no current will flow up to a certain level. After an increase of voltage, current will increase abruptly. This is called avalanche breakdown of a diode. The reverse bias increases the electrical field across the depletion region. When the high electric field exists across the depletion region, the velocity of the minority charge carriers crossing the depletion region increases. These carriers collide with the atoms of the crystal. Because of the violent collision, the charge carriers takes out the electrons from the atom. The width of the depletion region varies. Their width depends on the bias applied to the terminal of the p-n junction. The collision increases the number of electron-hole pairs which are quickly separated and collide with the other atoms of the crystal. This process is continuous and the electric field becomes so much higher than the reverse current starts flowing in the p-n junction. This process is known as avalanche breakdown. After the breakdown, the junction cannot regain its original position because the diode is completely burnt off. The IV characteristics of the avalanche breakdown give us a lot of detail. The avalanche breakdown happens due to the saturation current in the reverse bias. So, when we amplify the reverse voltage, the electric field will automatically increase. If the reverse voltage and the width of the depletion layer are VA and D, then the electric field which is generated can be measured using the formula EA is equal to VA by D. These mechanisms will occur in p-n junctions which are lightly doped where the depletion region is somewhat extensive. The density of doping regulates the breakdown voltage. In avalanche breakdown, temperature coefficient increases. As the temperature increases, magnitude of the breakdown voltage also increases. Let us look at some of the differences between the Zener and the avalanche breakdowns. First, the definition. The flow of electrons across a p material barrier of the valence band to the evenly filled n-type material conduction band is the Zener breakdown, whereas an avalanche breakdown is the occurrence of raising the flow of electric current or electrons in insulating material or semiconductor by giving a high voltage. The next difference is based on doping and the depletion region. In Zener breakdown, we have high doping and a thin depletion layer, whereas in the avalanche breakdown, we have normal doping and thereby the depletion region width is really wide. The electric field applied is strong in the case of the Zener diode, whereas weak in the case of the avalanche breakdown. The reverse potential is low for the Zener breakdown and high for the case of the avalanche breakdown. The temperature coefficient is negative for Zener breakdown and positive for the avalanche. The charge carriers which are generated for the Zener breakdown are electrons, whereas electrons and holes are generated for the avalanche breakdown. The ionization occurs due to the application of an electric field for the Zener, whereas it is due to the collision of the charge carriers with the atoms for the case of the avalanche breakdown. Then, the breakdown voltage is inversely related to the temperature for Zener breakdown and it remains constant after the breakdown. While in the case of the avalanche breakdown, the breakdown voltage is directly proportional to temperature and the reverse voltage may vary. The VI characteristics of the Zener breakdown show a sharp curve and is thereby used for voltage regulation, whereas for the avalanche breakdown's IV characteristics, a sharp curve is not obtained and it is useful for rectification purposes. Let us look at an analogy of the Zener and Avalanche breakdowns. Here we see a normal road with a car going by. This car will just go by from the left to the right. But if the car is supposed to move from the right to the left, there is going to be permanent damage to the car as well as the road. This is what is avalanche breakdown. Now consider a road which is smooth and elastic. The car very easily moves from the left to the right, while the movement of the car from the right to the left is going to be not so bad as in the case of the car which went on the normal road. Here we have a summary of the avalanche and the Zener breakdowns. From the above information, we can conclude that generally there are two different breakdowns which are distinguished based on the concentration of doping bias in the p-n junction. Whenever the p-n junction is doped highly, then Zener breakdown will happen, whereas when the avalanche breakdown occurs due to a lightly doped p-n junction. Thank you for your patient listening. If you like this video, I'll encourage you to like, subscribe and share it with your friends. Thank you.